Hello everyone, hope you all are doing good. I am Anjana from LearnoHub, the free learning platform where you can study math, science and SST absolutely free at learnohub.com. In today's class, we are going to discuss ICSE Class 10 Physics Chapter 8 Current Electricity. We'll be discussing about electromotive force, terminal voltage, internal resistance and the combination of resistors. What are the two different types of combination of resistors? Related to this, we'll be solving problems. Are you all ready? Let's begin. First, let us understand what an electric cell is. You can just look at this figure. Here, what is happening? We have a battery or a cell which is connected using wires to a bulb. Okay, the electric current starts flowing through it and the bulb glows. Just a simple circuit we have. Okay, you can take a battery, a simple LED bulb and two wires. Okay, if you connect this, you will see that the bulb will start glowing. What is actually happening here? Here electrons are flowing or current is flowing. We have studied this. Okay, now what does this battery or a cell do? In cell which is represented in this way, and many cells which are joined together will form a battery, whatever it is, a battery or a cell. Okay, in an electric cell or a battery, what is happening here? The chemical energy is getting converted into electrical energy. Okay, chemical energy gets converted into electrical energy. That is, this cell or a battery is storing this chemical energy, okay, which is then converted to electric energy. Okay, now what is an electric cell? You can define an electric cell. Here, they maintain a potential difference. We have a positive and negative terminal. They maintain a potential difference between them. Okay, so electric cell maintains a constant difference in potential between the two conductors by a chemical reaction to obtain a continuous flow of charge between them. And this potential difference helps in the flow of charge. When charges flow, there is current. Okay, so we'll understand this in detail. To understand electromotive force, consider this cell. This is a cell in open circuit. We have not connected a bulb or resistor, anything. Just a simple cell we have. Here we have an aqueous solution. This aqueous solution is dilute sulfuric acid. Okay, dilute sulfuric acid solution is taken and two electrodes are dipped into it. That is, a copper rod and a zinc rod is dipped inside this. Okay, now there is dissociation of these sulfuric acid ions. It dissociates into H plus ions and sulfate ions. Okay, H plus positively charged, sulfate ions are negatively charged. This negatively charged ion move towards the zinc electrode. Okay, they move towards the zinc electrodes and gets accumulated on the zinc electrodes. Positive charges move towards the copper electrode and gets accumulated here. So due to this accumulation of negative charges, this zinc electrode becomes negatively charged and this negatively charged electrode is called anode. Okay, this is called anode. And here the positively charged electrode is called cathode. Okay, so here due to the difference in potential, one electrode is positively charged and the other is negatively charged. Here there is an accumulation of electrons, negative charges are present. Here there is a loss of electrons happening. Okay, so because of this difference in potential, a potential difference is created. Now what is this potential difference? Let's see. When this circuit is connected, when this simple cell is connected to a circuit, what happens? Here charges starts flowing. Okay, this flow of charges or the flow of current is happening due to the presence of a cell. Okay, the cell maintains a potential difference. Due to this potential difference, what is happening? The current or charges are flowing. Okay, so there is a work done in moving the charges. Okay, this work done to move positive charges will be called the EMF of the cell. Okay, we can define EMF. EMF of a cell is defined as the energy spent or the work done per unit charge in case of one charge in taking a positive test charge around the complete circuit of the cell. That is, in the circuit outside the cell as well as in the electrolyte inside the cell. So here inside the cell there is movement of electrons and also there is movement of charges when it is connected to a circuit. Okay, the work done in taking a test charge Q around the complete circuit of the cell, then EMF of the cell can be represented by the letter epsilon. Okay, capital epsilon is used to represent EMF. We have said that it is the work done to move positive test charge. Therefore, W divided by Q, where W is the work done and Q is the charge which is moved. Okay, so EMF is a potential difference as we said, therefore volt will be its unit, which is represented by capital V. Okay, now how to measure this? In order to measure this, you can use a high resistance voltmeter, or you can use a potentiometer in order to measure the value of EMF. Clear? So understood what EMF is? EMF is called, the full form is electromotive force. Okay, this is not a force, it is a potential difference. It is a voltage, electromotive force. Clear? And this force, this electromotive force helps the movement of charges or the current flow in a circuit. Factors affecting the EMF of a cell. Okay, EMF of a cell. When you take a battery, when you buy a battery, let's say this battery has positive and negative terminal, and on it will be shown that 15 volt battery. So this 15 volt, this value is the EMF of cell. Okay, for a material, the material of the electrodes is one point on which the EMF depends. Okay, so EMF of a cell depends on the material of the electrodes used. And the second is the electrolyte, the H2SO4 which you used in the previous cell. So electrolyte which is used. On these two factors, the cell's EMF depends. Now what are the factors on which it doesn't depend? One is the shape of the electrodes. What shape electrodes are used? It doesn't depend on that. Next is the distance between the electrodes. If two electrodes are placed in this manner, okay, if you increase the distance between these electrodes, there is no change happening. It will be the same. Okay. Now the amount of electrolyte in the cell. Amount of electrolyte, the volume of electrolyte, let's say 1 liter of H2SO4 or 0.5 liters of H2SO4. So there is no change going to happen in this case. So whatever be, the dissociation of the ions should happen. Only that much. Okay. If dissociation happens, there will be the anode and cathode produced, and the movement, there is a potential difference created, movement of charge will happen and the current will flow in the circuit. Okay, so these are the factors on which the EMF depends and the factors on which the EMF is independent. Terminal voltage of a cell. We have studied about EMF. Now, when you have a cell, okay, we have studied a cell in open circuit. Now, this cell is connected to a bulb or it is connected to a resistor. Then it becomes a closed circuit. So, this cell is in a closed circuit. Here we have the dilute sulfuric acid as the electrolyte. You have the electrodes, anode and cathode. This cell, there is a potential difference between the anode and cathode developed. This forms a cell and the cell is connected to a resistor. Here we have a resistor. What happens? There will be flow of charges. Okay, there will be flow of charges and there will be flow of current. So now what is terminal voltage? In this case, you will be considering only the flow of charges outside the cell. You won't be considering what happens inside the cell. Okay, EMF is when both outside and inside, whatever is happening should be considered as a total. But when it comes to terminal voltage, there is flow of charges. Okay, and the work done in moving a positive test charge outside the cell, okay, or around the cell in a circuit is called the terminal voltage. Clear? So we can define terminal voltage. The terminal voltage is a cell is defined as the work done per unit charge in carrying a positive test charge around the circuit connected across the terminals of the cell. Just remember this. When you take the case of EMF, you will be taking both inside and outside, whatever happens. But when it comes to terminal voltage, you will have to consider only outside the cell. Okay. Now, terminal voltage is represented by capital letter V. Okay. Then the unit will be volt, represented by capital V. Okay. Then terminal voltage, it is a work done which can be represented as W dash. Okay. Work done by charge, unit positive test charge. So this is how you can find the terminal voltage. So why W dash? This work done and the work done which we have discussed in case of EMF is different. Okay, there both the work will be considered. That is inside the cell the charges movement and the movement of charges outside the cell. Here we will be considering only the movement of charges outside the cell. Clear? Voltage drop in a cell. We have studied about EMF and terminal voltage. One thing that we can understand is that EMF is greater than terminal voltage. What is the reason? Why is EMF greater than terminal voltage? EMF greater than terminal voltage. What is the reason? When you consider EMF, you are considering the work done inside the electrolyte, inside the cell and the work done outside the cell. to move the charges. But when it comes to the case of terminal voltage, we are just considering the movement of charges, the work done in moving charges outside the cell. Inside the cell, whatever happens is not matter. Okay, so that the EMF will always be greater than the terminal voltage. Now the difference, that is, here there is a work done in moving a unit positive test charge inside the cell. Okay, inside the cell, inside the electrolyte, for the movement of charges, a work is done, and this work is the voltage drop. Okay, here we know that the chemical energy is getting converted into electrical energy. Okay, so due to this motion of charges, chemical energy gets converted into electrical energy, and that time what is happening? There is a loss of energy, and this energy appears as heat. So we can define voltage drop, the work done per unit charge in carrying the positive test charge through this electrolyte is called the voltage drop in the cell. Voltage drop will be representing with small letter v. Again, the unit is volt, represented by capital V. Okay, small letter v and capital V is the unit of this. Okay, now let's say small w is the work done in this case. Work done in moving unit positive test charge inside the electrolyte. Okay, charge is represented by Q. Then you will be having voltage drop. V is equal to W divided by Q. Small w divided by small q. Okay, this is how you will be getting the potential drop or the voltage drop in a cell. Relationship between EMF and terminal voltage of a cell. We have studied what EMF is. EMF is equal to work done divided by charge. Here the work done is to move the charge through the entire circuit. Okay, then we have studied what terminal voltage is. Terminal voltage V is equal to work done W, that is across the terminals to move the charges. What work is done divided by charge Q, unit positive test charge Q. We have studied the voltage drop. Small b is equal to work done in moving the charges in the electrolyte divided by Q. Okay, we have studied law of conservation of energy. So here the work done, total work done will be the work done outside the cell plus the work done inside the cell. Okay, total work done will be work done outside the cell plus the work done inside the cell. Now, we have studied the law of conservation of energy. What is the statement? Energy can neither be created nor be destroyed but can only be transferred from one form to another. So, applying here, you will be getting W is equal to W dash plus small letter w. Okay. Now, what we are going to do is, we are going to divide throughout with charge Q. Then, W by Q is equal to W dash divided by Q plus small w divided by Q. Okay, what is W by Q? W by Q is the EMF. EMF is equal to W dash by Q. W dash by Q is the terminal voltage plus small w by Q. Small w by Q is the voltage drop. Okay. So, this is the relation. EMF is always equal to terminal voltage plus the voltage drop. If you need to find the voltage drop, then voltage drop is EMF minus terminal voltage. Or terminal voltage will be equal to EMF minus voltage drop. Now, just by looking at this equation, we can understand that when the terminal voltage increase, the voltage drop should decrease. Okay, to maintain EMF value. So, EMF value, as we said, for a battery, EMF is a constant. If it is a 15 volt battery, then the EMF is not going to change. It will be a constant value. So, the terminal voltage and voltage drop can change. If the terminal voltage increase, then the voltage drop will decrease. Okay. In case we have a circuit and the cell will be drawing more current. In that case, what happens? The voltage drop is going to increase. Okay, and the terminal voltage will be less. Voltage drop will be more because to move the electrons within the cell, it is taking more energy. Okay, more potential difference will be there. Understood the relation? Next, the difference between EMF and terminal voltage. Very important 3 points that you have to study for comparison. Okay, EMF. First, EMF, it is measured by the amount of work done. That is simple statement. We have defined the definition you will be giving first. Okay, it is measured by the amount of work done per unit charge in moving a positive test charge in the complete circuit inside and outside the cell. Okay, inside and outside. When it comes to terminal voltage, how is it? It is measured by the amount of work done per unit charge in moving a positive test charge in the circuit outside the cell. Only outside. Inside is not considered. Now the second point we'll discuss. It is a characteristic of a cell. We have said that when you take a battery, 15-volt battery, it is a constant value. It's not going to change. That is, it does not depend on the amount of current drawn from the cell. Whatever current is drawn from the cell, EMF will remain the same. Okay. When it comes to terminal voltage, what happens? Depending on the current drawn from the cell. If more current is drawn from the cell, what happens? Then the voltage drop is going to increase and terminal voltage will be small value. Okay, it depends on the amount of current drawn from the cell. More the current drawn from the cell, less is the terminal voltage. Okay, now the third point, it is equal to the terminal voltage when the cell is not in use. Okay, whether the cell is used or the cell is not used, what is that? There is EMF. Okay. Now, if the cell is not used, in that case, there is not going to be voltage drop. Then the EMF and terminal voltage will be the same. It is equal to the terminal voltage when the cell is not in use. Okay. While greater than the terminal voltage when the cell is in use. When cell is used, what happens? Voltage drop. There will be voltage drop and terminal voltage. Okay. Then the EMF will be the sum of terminal voltage and voltage drop. If there is no voltage drop, in that case, that is the cell is not in use. In that case, EMF and the terminal voltage will be the same value. Okay. When it comes to the comparison here, the third point, it is equal to the EMF of a cell when cell is not in use. The same point here you are giving. Okay. When the cell is not used, then the terminal voltage and EMF will be having the same value. While less than the EMF when the cell is in use. When the cell is used, it will be less than the EMF. Clear? What is internal resistance of a cell? When you consider a cell, here you can see that there is flow of charges, there is movement of ion. Due to this movement of ion, there will be collisions, okay? And due to this reason, some resistance will be developed. It is not free of resistance. Inside the cell, some resistance will be developed. This resistance that is developed inside the cell is called the internal resistance. Internal resistance is usually represented this way. Here you have the cell and this resistance is your internal resistance. That's normally connected to a circuit. This is a normal resistor and the smaller R is used to represent internal resistance. Okay, how internal resistance is created? Because of the movement of ions. Inside the cell, you know that due to the movement of ions, there is a work done. Okay, but outside, how is it happening? Due to the movement of electron, due to the movement of charges. Here you can see that the current will always flow from the positive to negative terminal. We know the charges are moving from the negative to positive terminal and the current will be in the opposite direction, in the direction of movement of the positive ion. Current will be from positive to negative terminal. Okay, but inside the cell, the ions are moving. Due to this ions motion, there will be collisions and some resistance will be developed and this resistance is called the internal resistance. Okay, so internal resistance, the resistance offered by the electrolyte inside the cell to the flow of current is called internal resistance. Okay, now internal resistance represented by small r, we know that the current flow will be the same. Okay, I into R. So this I into R will give you the voltage drop. We know that inside the cell, the potential difference will be the voltage drop. Okay. Here, voltage drop will be equal to the current that is flowing into the internal resistance. You can calculate internal resistance in this way. And what is the unit of resistance? We know the unit of resistance is ohm. Therefore, the unit of internal resistance is also ohm. Relationship between EMF, terminal voltage and internal resistance. How to find internal resistance when EMF and terminal voltage is known? So, in a circuit, we have a cell. This is the internal resistance. This is how you represent. Then you have a normal resistance of resistor R. Okay, a resistor of resistance R. Here the voltage will be, the terminal voltage is V. We are taking EMF of the cell is represented by epsilon. Then you have an internal resistance, small letter R. Okay, we know that the current I will be equal to voltage divided by resistance. So here the total voltage, what is the total voltage? Total voltage will be the EMF. Okay. Then total resistance. What is the total resistance in this case? Here we have an internal resistance and the normal resistance. Okay. So total voltage will be the EMF value and the total resistance is capital R plus small r. Okay. So current I is equal to epsilon divided by capital R plus small r. You can write this as EMF equal to I into capital R plus small r. Okay. Now what is I? I is the current that is flowing. Okay. So relating it to the terminal voltage. Terminal voltage is related to the normal resistor. Internal resistance is not considered. We'll be having current I is equal to terminal voltage V divided by resistance R. Same current is flowing through this internal resistance also. Okay. You will be having I is equal to V divided by R. Substituting here, we get epsilon equal to V divided by R. We need a relation between EMF. EMF is already here. Internal resistance and terminal voltage. Internal resistance also is here. So we need to bring the terminal voltage. So this is how you can bring terminal voltage into this equation. V by R, R plus R. Okay. Now epsilon is equal to VR divided by R plus V small r divided by R. Removing the brackets and multiplying. Capital R can be cancelled. Okay. What we need is small letter r. Okay. So VR divided by R will be equal to epsilon minus V. Taking this V to the opposite side becomes minus V. Now next what to do? Okay. Keeping the internal resistance R value in the left hand side, taking all other terms to the opposite side. Here we have V by R, reciprocal, taking the reciprocal and multiplying. We get R divided by V into epsilon minus V. Okay. That is R into epsilon by V minus V divided by V. V and V are the terminal voltage, same value, so it becomes 1. So that is internal resistance R is equal to capital R into epsilon divided by V minus 1. Okay. So this is the relation between terminal voltage, EMF and the internal resistance. When terminal voltage and EMF is known, you can easily calculate what the internal resistance is. Clear? Next, the factors affecting internal resistance of a cell. First one is the surface area of the electrodes. So electrodes we have studied, cathodes and anode. Okay, here when you have two electrodes, if the surface area of the electrodes consider, this is the surface area. Okay, surface area, when the surface area increases, internal resistance is going to decrease. That is, there is an inverse proportional. Okay. Now the second point, the distance between the electrode. When you increase the distance between the two electrodes considered, when the distance increases, what happens to internal resistance? Internal resistance is going to increase. Directly proportional. Distance increases, internal resistance is also increasing. Now the third point, the nature and concentration of the electrolyte considered. Concentrated electrolyte if you are using. When the concentration increases, internal resistance will also increase. Why? Because there is more ions in this case. Okay, movement of ions will increase, collisions will increase, and therefore the internal resistance will also increase, directly proportional. Now fourth one, the temperature of the electrolyte that is considered. Okay, when the temperature of the electrolyte considered increases, okay, temperature increases, internal resistance is going to decrease. So in these two cases, that is first and fourth cases, surface area increases, internal resistance decreases, and when temperature increases, also temperature of the electrolyte increases, internal resistance decreases. Clear? Combination of resistors. To get a desired value of resistance, we will have to combine resistors. So there are three ways in which the resistors can be combined. The first is series combination, second is parallel combination, and the third is both in series and parallel. If you need to increase the resistance, in that case, we will be considering the series combination of resistors. If you have to decrease the resistance, then parallel combination of resistors will be considered. First, let's see the combination of resistors in series. How resistors are combined in series? You can see three resistors, R1, R2, R3. They are end-to-end connected. That is, this is the first end of the resistor 1, which is connected to a point A. Then the other end is connected to the second resistor B. Okay, at the point B, R2 and R1 are connected. Okay, the end of R2, the second end of R2 is connected to R3 and the end of R3 is connected to a point D. Okay, so this is a complete circuit. You have a battery, you have a key. Okay, so when the key is plugged in, what happens? Current starts flowing through the circuit. Here we have the positive terminal and this is a negative terminal. Now you will have to remember one point. Here at this point A, there will be high potential. Okay, because the positive terminal is connected to A. Okay, so here we will be having a high potential and at D, the potential will be the lowest, low potential region. Okay. So what about the current? Here you will have to remember one point. In case of series connection, the current flowing through the circuit will be same. Okay, current across R1, current across R2 and the current across R3 will be the same. Same current will flow through all the three resistors. Okay, what about potential difference? So if you take the potential at each point, let's say VA is the potential at A, at B the potential is VB, at C it is VC and at D it is VD. As we said, the potential is highest at the point A. VA will be greater than VB, greater than VC, greater than VD. Okay, if the potential difference at R1, we are representing it as V1. We know potential difference will be the high potential minus low potential. Okay, at R1, the potential difference V1 will be equal to VA minus VB. What about V2? The potential difference along the resistor R2 will be equal to VB minus VC and V3 will be equal to VC minus VD. Okay, this is how you will be getting the potential difference. Now, what about potential difference? We have understood that the current is same through all the resistors, but the potential difference will be different. Okay, it depends on the resistance. How is resistance and potential difference dependent? We have V is equal to IR according to Ohm's law. V is equal to IR. Okay, here we are saying that the current is a constant. Current across R1, current across R2 and current across R3 are the same. We will represent it as I. Which means we can say the potential difference is directly proportional to resistance. If the resistance increases, potential difference increases. So in this case, which resistor has the highest resistance, there the potential difference will also be high. Okay, so this is a series combination of resistors. In order to get the potential, the total potential, here we have said that the current is same. The total potential V will be equal to potential V1 across the resistor R1 plus potential V2 across the resistor R2 plus potential V3 across the resistor R3. So this will give you the total potential difference. Now let's see how to find the equivalent resistance. How to find the equivalent resistance in case of series combination of resistors. So here you can find three resistors are connected in series across a battery. This is your battery. Here we have the potential difference and current is flowing through the circuit when the key is plugged in. Now what happens? The same current, as we said, same current flows through all the three resistors. What about potential difference? We have discussed, we have three potential difference, V1, V2 and V3. So this is a case when we are using three resistors, V1, V2, V3. Okay, what is V1? We have Ohm's law according to which V is equal to IR. Okay, V is equal to IR. Then what is V1? Take this case, here we have the resistor R1. Across R1, we have the potential difference V1, which means here the V1 will be equal to current I into the resistance R1. Okay, what about V2? V2 will be equal to current I into resistance R2 because potential difference across the resistor R2 is V2. What about V3? V3 will be IR3. Okay. Now we have V is equal to IR. As we said, the total potential difference will be the sum of potential difference across each resistors. V will be equal to V1 plus V2 plus V3. What is V? V is the potential difference of the battery. Okay. Here V will be equal to the total current I into the equivalent resistance. Equivalent resistance, which is represented as Rs in case of series combination. I into Rs, which is equal to V1. V1 is IR1. Okay. IR1. What is V2? V2 is IR2. And V3 is IR3. Okay. So here, taking I common, you will be getting R1 plus R2 plus R3, which is IRS. Okay, I can cancel this I from both the sides, which is common. Then RS is equal to R1 plus R2 plus R3. So this is how you can find the resistance, the effective resistance in series combination. RS is R1 plus R2 plus R3. If you are having just two resistors of resistance value R1 and R2, then RS will be equal to R1 plus R2. If you have n number of resistors of resistance value R1, R2, R3, R4, etc. up to some Rn. In that case, you will be getting Rs, the effective resistance in series combination, equal to R1 plus R2 plus R3 plus etc. plus Rn. Just you have to take the sum of resistors. If in this case, we have 1 ohm, 2 ohm, 3 ohm, 3 resistors. Okay, then what is Rs? Rs will be equal to 1 plus 2 plus 3, which is equal to 6 ohm. Very easy, right? Now consider a case, 3 resistors of equal resistance value is taken. Let's say of value R. 3 resistance of R ohm resistance. In that case, it is very easy to find what is the effective resistance. We have Rs is equal to, if R1 plus R2 and R3 are the 3 resistors. Here we are saying that all 3 resistance have the same value. In that case, Rs will be equal to R plus R plus R, which means Rs is equal to 3R. What is 3? 3 is the number of resistors. Therefore, if you have n number of resistors of equal resistance, in that case, the effective resistance in series combination will be equal to n times the resistance of each resistor. Okay. Rs is equal to n into R. For example, let's take 3 ohm resistors. Okay, 3 ohm resistance, you have 5 resistors of 3 ohm. Then what is Rs? Rs will be equal to 5 into 3 ohm, which is 15 ohm. Clear? Next is the combination of resistors in parallel. Here you can see 3 resistors, R1, R2, R3. When you take the ends of these 3 resistors and connect 2 common points. Okay, here you can see this is the end of the first resistor. Second resistor and third resistor, they are connected to a common point A. Similarly, this end is connected to a common point B. Okay. Now, this is a complete circuit. You are having a battery. You have a key. When key is plugged in, what happens? The electricity starts flowing through the circuit. Now, you can see the current which reached this point. Here, what is happening to the current? The current is splitting in 3 directions. The current starts flowing through R1, R2 and R3. Here, depending on the resistance value, there is different current. It is not the same current as in case of series connection. The flow of current is split into 3 portions. Okay. So, here the total current will be I1 plus I2 plus I3. When you take the sum, I will be equal to, total current will be equal to I1 plus I2 plus I3. What about potential difference? Here we can see this end A is connected to the positive terminal of battery. So here the potential is VA. What about end B? End B is connected to the negative terminal of battery. So here point A is at high potential and point B is at low potential. Now the potential difference V will be equal to high potential minus low potential. V is equal to VA minus VB. You have to remember this point. Here in parallel combination, the same potential difference will be there across each resistors. Okay. The potential difference across R1 will be equal to V. Potential difference across R2 will be V. And potential difference across R3 will also be equal to V. Okay. Now the current. How is current, potential difference and resistance related? According to Ohm's law, we have V is equal to IR. As we said here, V is a constant. We have I is equal to V by R. If V is a constant, we can write I is inversely proportional to resistance, which means when resistance increases, I decreases, and when resistance decreases, I value increases. Okay, so here in this case, the current I1 across the first resistor R1 will be equal to V divided by R1. Okay, because I is V by R, which means here the current will be V divided by R1. Here it is V by R2 and here V by R3. Okay, so to remember this point, in series combination, current is same, potential difference is different. In case of parallel combination, current will be different, potential difference will be same across all the three resistors. Next is the expression for equivalent resistance in parallel. We have studied the expression RS for equivalent resistance in series. Now let's find the equivalent resistance in parallel. How to find equivalent resistance in parallel? We have the same circuit as we said. Here in the circuit we will be having current I1 is equal to V divided by R1, I2 is V by R2 and I3 is V divided by R3. Okay, we have the total current I is equal to I1 plus I2 plus I3. Here at this junction, what is happening? The current is splitting into I1, I2, I3. I current is splitting into I1, I2 and I3. Okay, now the total current I will be equal to the potential difference V, which is a constant in this case, divided by the equivalent resistance Rp. Okay, equivalent resistance in parallel combination is represented as Rp. So I will be equal to V divided by Rp. Okay, we have I1, I2 and I3 values. Now substituting, we get V by Rp is equal to I1 is V divided by R1, I2 is V by R2 and I3 is V divided by R3. Okay, here V divided by Rp is equal to, V is common, 1 by R1 plus 1 by R2 plus 1 by R3. Okay, V and V can be cancelled. Then what do we get? 1 by Rp is equal to 1 by R1 plus 1 by R2 plus 1 by R3. So this is how you can find the equivalent resistance in parallel. Okay, now if you have two resistors R1 and R2 which are connected in parallel, in that case you will be having 1 by Rp is equal to 1 by R1 plus 1 by R2. If you have four resistors, then 1 by Rp will be 1 by R1 plus 1 by R2 plus 1 by R3 plus 1 by R4. N resistors, 1 by Rp will be 1 by R1 plus 1 by R2 plus 1 by R3 plus etc. up to 1 by Rn. Now here a simple formula can be formed. 1 by Rp will be equal to, taking the LCM of denominator, we get R1, R2 in the denominator, numerator. Here we have R1, R1 into R2. We will be getting R1, R2. So R2 into 1 is R2 plus R1. Okay, so what is Rp then? Taking the reciprocal. Taking the reciprocal on both sides, we get Rp is equal to R1, R2 divided by R1 plus R2. Okay, so to find the equivalent resistance in parallel, when you know the resistance value, first take the product of the resistance value, you will be getting the numerator, and sum of the resistance value will be giving you the denominator. This is the case only when two resistors are taken into consideration, not in all cases. Okay, now if you have n number of resistors of resistance value R, how to find Rp? Total resistance. We have 1 by Rp is equal to 1 by R1 plus 1 by R2 plus etc. plus 1 by Rn. Okay, all the resistors are of resistance value R. In that case, we will be getting 1 by Rp equal to 1 by R plus 1 by R plus 1 by R plus etc. plus 1 by R. Okay, so 1 by Rp will be equal to, here denominator is same. What about numerator? 1 plus 1 plus 1 plus 1. How many 1 will be there? N times. Okay, now take the reciprocal. Rp will be R divided by N. If you have 4 resistors of resistance value 20 ohm. Okay. Then what is Rp? Rp will be equal to R divided by N. In series combination, N into R. In parallel combination, R by N. Okay. So, R is 20, N is 4. Then you will be getting 5 ohm. This is how you can find the equivalent resistance in case of parallel combination of resistors. By now we have studied what the series combination and parallel combination of resistors is. If you have two resistors R1 and R2, then when they are connected in series, that is first resistor and the second resistors are connected in series, the effective resistance Rs when calculated will be the sum of these two and it will be greater than R1. Also, it will be greater than R2. Okay, this is how about series combination. We have studied the parallel combination. How in parallel combination, this is how the resistors are connected. So, here R1, R2. Okay, when you take the effective resistance Rp, it will be less than R1. Also, Rp will be less than R2. Okay, so remember this. The effective resistance in series will be greater than the resistance values of both the resistor. Whereas in case of parallel combination, the effective resistance Rp will be less than both the resistance values of the resistors. Okay. Now, if you need a value that is between this, okay, between R1 and R2, if you need a value or you need some other values, okay, in that case, we'll be using a combination of series and parallel. Let's take some cases. So, here, this is the first resistor. This is your second resistor. This is the third resistor and these resistors are connected to the circuit. Okay, this is how the combination is. Here you can see two resistors. This is R1, R2, R3. How is R2 and R3 connected? R2 and R3 are in parallel. Okay, what about R1? R1 is connected in series with the effective resistance of R2 and R3. Okay. So, here what you will have to do is, first you have to solve this part. That is, you will have to solve the parallel first. So, if a combination of resistors are given, you will have to solve the parallel part first. Okay. After solving this parallel part, you will have to add them to get the effective resistance. So, here what is Rp? We have Rp is equal to R2 R3 divided by R2 plus R3. If there is only two resistors, we know how to find the effective. Okay. Now, how to find the Rs value? Now, you can draw an equivalent circuit. Equivalent circuit is when you will find the effective resistance here and you can just represent it as a single resistor. Okay. So, the effective resistance can be calculated after drawing an equivalent circuit. It's not necessary that you draw an equivalent circuit, but to simplify, you can draw an equivalent circuit. So, this is how the equivalent circuits look like. So, here you will have the first resistor R1. This is your second resistor R2, which is this value, that is Rp value, okay, connected to the circuit. Okay. Now, to get Rs, Rs will be equal to R1 plus Rp. When you add these, you will be getting the Rs value. For example, if R1 is equal to 2, R2 is equal to 2 and R3 is equal to 2. Okay. R1, R2 and R3 are equal to 2. In this case, let's find what is the effective resistance of the circuit. How to find? First, you will have to solve this part, which is Rp is equal to R2, R3 divided by R2 plus R3 equal to 2 into 2 divided by 2 plus 2, which is 4 by 4 equal to 1 ohm. Okay, 1 ohm is the value. Now, what about Rs? Rs is R1 plus Rp. R1 is equal to 2 ohm. 2 plus 1, which is 3 ohm. Okay, 3 ohm is the value that we are getting. Okay. When these are connected in series, if 3 resistors are connected in series, what is the effective value? 2 ohm, 2 ohm, 2 ohm. What do we get? We'll be getting 6 ohm on adding this. R1 plus R2 plus R3, you get 6 ohm. Okay. When they are connected in parallel, what is the value? 2 ohm, 2 ohm, 2 ohm. How to find? we'll be having 1 by Rp is equal to 1 by 2 plus 1 by 2 plus 1 by 2. 1 by Rp is equal to LCM 2, denominator 2, numerator 1 plus 1 plus 1, which is 3 by 2. Then Rp will be equal to 2 divided by 3. You will be having 0.667. This will be the value. Okay. Now you can see this is a small value. Here we are getting a higher value. And this 3 ohm. Okay, when there is a combination of series and parallel, you will be getting a value which is in between the Rp and Rs values. Clear? We have some important points to be discussed. The first one, for the two resistors joined in series, the equivalent resistance is more than when they are joined in parallel. If you have two resistors, R1 and R2. Okay, this is the series combination and this is the parallel combination. Okay, R1, R2, R1, R2. Okay, we know that the effective resistance in series combination will always be greater than the effective resistance in parallel combination. Now, we have studied about the VI graph and IV graph. Okay, this is the IV graph. Voltage along the x-axis and current along the y-axis. What does the slope of this graph give you? Slope of the graph will be giving you the conductance, which is equal to delta I by delta V. Okay. Now, with the slope, how to connect it with the resistance? We know slope is conductance, which means the slope will be equal to 1 by resistance. Okay. That is, when slope increases, what happens to resistance? Resistance decreases. Slope increases, resistance decreases. Now my question is, here we have Rs and Rp. Rs is a higher value. Okay, which one will be having greater slope? So here, when you take a graph, Vi, I have considered two slopes. Okay, this is having higher slope, smaller slope. Which one will be for parallel combination of resistors and the effective resistance for series combination? Now tell me, here slope is high. When slope is high, resistance will be low. Resistance is low for the parallel combination, Rp. This is the slope of parallel combination effective resistance. And this is the slope for series combination effective resistance. Okay. Now when you take the VI graph, voltage along the y-axis and current along the x-axis. What does the slope give you? Slope of VI graph will give you the resistance directly. Okay, you will be getting the resistance value when slope is taken. Okay. Now here we know that when slope increases, what happens to resistance? Resistance also should increase. So higher slope, higher resistance value. Okay. So when you take a graph, this is your VI graph, you have two slopes. Which slope will be for Rs and which one will be for Rp? Here, higher slope, higher resistance. This is higher slope, so higher resistance is Rs. Okay, smaller resistance is Rp. This is how the graph look like. So, important point to remember is in series and parallel combination, when you take the effective resistance, always the series combination effective resistance will be greater than the parallel combination effective resistance. If two resistors are taken R1 and R2, then the series combination effective resistance will be greater than the highest value. Okay. Here if it is 2 ohm and this is 3 ohm, then you will be getting 5 ohm, which is greater than the highest value. Okay, greater than both the values, even it will be greater than the highest value. When you take for parallel combination of resistors, when you take the effective resistance, the value will be lower than the Rp value will be lower than the smallest resistance. Okay. Second one, what happens to the current or how to find the current across each resistances if current I is divided into two resistances R1 and R2 connected in parallel. Consider two resistors which are connected in parallel. So this is the first resistor R1. This is your second resistor R2. They are connected in parallel. Okay. So a current that reaches this point, what happens? It splits into two. I1 flows through the first resistor R1 and I2 flows through the second resistor R2. We know that in a parallel combination of resistors, the voltage will be same but current will be different. Okay, so to get the total current is splitting into I1 and I2. Therefore, I will be the sum of I1 and I2. So this is your first equation. Okay, now the second one, we know the potential difference will be same. Potential difference across each resistor will be same, which means if the potential difference we take as V1 across R1 and across R2, if you take it as V2, will be equal to V. The same value will be getting. So V1 will be I1 R1 and V2 will be I2 R2. Okay, therefore I1 R1 is equal to I2 R2, which is your second equation. Now we need to find the current I1 across R1 and I2 across R2. How to find this? Let's see. So here in this equation, how do we get I1? I1 will be I2 R2 divided by R1. Before that, how can you replace this I2? Because we don't know the I2 value. We need to find I1. We don't know the I2 value. From the first equation, from equation 1, we will be having I2 equal to I minus I1. Okay, I2 will be I minus I1. So here we have I1 R1 is equal to I2 R2. In place of I2, you can substitute I minus I1. I minus I1 into R2. Okay, so I1 R1 is equal to, removing the brackets and multiplying, I R2 minus I1 R2. Taking this to the opposite side. Okay, I1 containing term is taken to the opposite side. Here there is a negative sign. It becomes positive. I1 R1 plus I1 R2 is equal to I R2. I1 is common. I1 into R1 plus R2 is equal to I R2 and I1 is equal to I R2 divided by R1 plus R2. So this is how you can find the current through resistor 1 R1. Okay, I1 is equal to I R2 divided by R1 plus R2. Then how to find I2? In order to find I2, you will have to take I1 is equal to I minus I2. Okay, I1 is equal to I minus I2. Take the same equation, I1 R1 equal to I2 R2. Now in place of I1, substitute I minus I2. I minus I2 into R1 is equal to I2 R2. Removing the brackets and multiplying, I R1 minus I2 R1 is equal to I2 R2. Okay, I2 containing term taken to the opposite side. I R1 is equal to I2 R2 plus I2 R1. I2 is common. I2 into R1 plus R2 is equal to I R1. Therefore, we'll be having I2 is equal to I R1 divided by R1 plus R2. Okay. I1 is I R2 divided by R1 plus R2 and I2 is I R1 divided by R1 plus R2. This is how you can find the current through each resistors. Clear? Next, third is when to find V1 and V2, that is voltage across the first resistor R1 and voltage across the second resistors R2 when the resistors are connected in series. Okay, in series connection. So here in series connection we know that the current will remain the same but the potential difference or voltage across the resistors will be different. So this is your first resistor R1, this is second resistor R2 which are connected in series. Okay, to a voltage source. To a battery it is connected. Now what happens? Current flows. The same current I will flow through R1 and R2. But the potential difference V will be different. Okay. So here across R1 you will be having V1 and across R2 you will be having V2. Okay. So the total potential difference V will be equal to V1 plus V2. Okay. V will be equal to V1 plus V2. We know that the current I1 is equal to current I2 which is the same I value. Okay. According to Ohm's law we have V is equal to IR. Okay. And what is I? I is V by R. So here what is I1? I1 will be equal to V1 divided by R1 and I2 will be equal to V2 divided by R2. So this is your first equation and this is your second equation. Okay, now take this equation. Here, in order to find V1, we will have to replace V2. What is V2 from the first equation? From equation 1, you will be having V2 is equal to V minus V1. Okay, now substituting in the second equation, we'll be getting V1 by R1 equal to V2 by R2. V1 by R1 is equal to V2 is V minus V1. V minus V1 divided by R2. Okay, cross multiplying, we get V1 R2 is equal to V minus V1 into R1. Removing the brackets and multiplying, what do we get? V1 R2 equal to V R1 minus V1 R1. Okay, taking V1 containing terms to the same side because we need to find the V1 value. V1 R2 plus V1 R1 is equal to V R1. Okay, V1 is common. V1 into R1 plus R2 is equal to V R1. And then V1 is equal to V R1 divided by R1 plus R2. So this is how you can find the voltage across the first resistor V1. Okay, VR1 divided by R1 plus R2, sum of the resistors. Now to find V2. How to find V2? Here we have V1 by R1 equal to V2 by R2. From equation 1, we have to replace V1. Okay, V1 in terms of V2 we need. Therefore, V1 will be equal to V minus V2. Substituting V minus V2 divided by R1 is equal to V2 by R2. Cross multiplying, we get V minus V2 into R2 is equal to V2 R1. VR2 minus V2 R2 equal to V2 R1. Okay, taking V2 containing term to the same side. VR2 will be equal to minus V2R2 becomes plus V2R2. V2R1 plus V2R2. V2 is common. Taking V2 outside. R1 plus R2. Which is equal to VR2. Then V2 will be VR2 divided by R1 plus R2. Okay, V2 is equal to VR2 divided by R1 plus R2. This is how you can find the voltage across resistor 1 V1 and the voltage across resistor 2. Let us take an example. A high resistance voltmeter measures the potential difference across a battery to be 9 volt on connecting a 24 ohm resistor across the terminals of the battery. The voltmeter reads 7.2 volt. Calculate the internal resistance of the battery. Okay. Here it is given that the voltmeter is of high resistance, which means it is supposed to draw no current. Okay. So this 9 volt will be the EMF. EMF is 9 volt. What else is given? Resistance is given. Resistance R is equal to 24 ohm. Okay, and the voltmeter reads 7.2 volts, which means the voltage is given. Voltage or potential difference V is equal to 7.2 volt. We have to calculate the internal resistance of the battery. Okay, we have studied a relation. EMF is equal to current I into resistance plus internal resistance. Okay, from this we are going to find what internal resistance is. According to Ohm's law, we have V is equal to IR, from which we can write I is equal to V divided by R. Here current value is not given. In order to substitute, to find internal resistance, we should put the values of EMF, resistance and the current I. Current I value is not given. Okay, we can write current I as V divided by R. We know the voltage, also we know the resistance. Okay, so this EMF will be equal to V divided by R into R plus R. Now removing the brackets and multiplying, we get EMF is equal to V into R by R plus V into small r divided by capital R. Okay, R gets cancelled. Then we have EMF is V plus VR divided by capital R. Okay, now we are going to form a relation to find R. We'll be having V small r by capital R is equal to EMF minus voltage V. Okay, taking this R to the opposite side, that is here we have V divided by R. Taking the reciprocal and multiplying, we get small r is equal to EMF minus voltage into resistance divided by voltage. Then we'll be having R is equal to E by V minus V by V is 1 into the resistance R. Okay, now put the values. Internal resistance is equal to EMF. EMF is given 9 divided by voltage is 7.2 minus 1 into 24, that is equal to, this can be written as 90 divided by 72. On cancelling we will be getting, we have 18 into 5 is 19 and 18 into 4 is 72. Okay, therefore 5 by 4 minus 1 into 24, which is, taking the LCM, denominator we get 4, 5 minus 4 divided by 4, which is 1 by 4 into 24, you will be getting the final answer 6. Okay, therefore the internal resistance is 6 ohm. 6 ohm is your internal resistance. Clear? Second example, 3 resistors of 2 ohm, 3 ohm and 4 ohm are connected in series and parallel. Draw the arrangement and find the equivalent resistance in each case. Okay, we have to connect the 3 resistors, 2 ohm, 3 ohm and 4 ohm in series and parallel. Okay, first let's see the series connection. In series, it is in the form of a chain. The resistors will be connected. Here we have the first resistor, second resistor, third resistor. Okay, 2 ohm, 3 ohm, 4 ohm. This is how the connection is. Okay, next, we can find the equivalent resistance in this case of series connection. Equivalent resistance Rs will be equal to, this is the first resistor, second resistor, third resistor. R1 plus R2 plus R3. Put the values. Rs will be equal to 2 ohm plus 3 ohm plus 4 ohm, which is equal to 2 plus 3, 5, 5 plus 4, 9. 9 ohm is the equivalent resistance in series connection. Okay, now the parallel connection. In parallel connection, we know the same amount of voltage will be there across all the resistors. Okay, the current will get split. So here, this is how you will be connecting the resistors in parallel. 2 ohm, 3 ohm, 4 ohm. So these are the terminals. This is your parallel connection of resistors. Now we'll find the equivalent resistance. Equivalent resistance in parallel. Okay. We have 1 by Rp is equal to 1 by R1 plus 1 by R2 plus 1 by R3. Since there are 3 resistors, you will be having 1 by Rp is equal to 1 by R1 plus 1 by R2 plus 1 by R3. 1 by Rp is equal to 1 by R1 is 2 plus 1 by 3 plus 1 by 4. So what is the LCM? 2, 3, 4. When you take the LCM, denominator you will be getting 12. Okay. 1 by Rp is equal to denominator 12. Numerator 2 into 6 is 12. 6 into 1 6 plus 3 into 4 is 12. 4 into 1 4 plus 4 into 3 is 12. 3 into 1 3. So here 6 plus 4 10. 10 plus 3 13. 13 divided by 12. 1 by Rp is 13 by 12, which means Rp will be equal to 12 divided by 13. Okay, what is 12 by 13? You will be getting 0.9 something. Okay, so Rp will be 0.9 something ohms. Understood? Next example, what resistance must be connected to a 15 ohm resistance to provide an effective resistance of 6 ohm? Here you can find R1. The first resistance is 15 ohm. Okay, and the effective resistance is given, which is 6 ohm. Okay, is it series connection or parallel connection? We know that in series connection, the effective resistance will always be greater than the resistance of each resistors considered. Okay, whereas in parallel connection, the effective resistance will be less than the resistors which are considered. So here we have 15 ohm as one resistor and the effective resistance is less than the resistance of the given resistor, which means the connection here is a parallel connection. Effective resistance in parallel connection is 6 ohm. We have to find the second resistance R2. Okay, we have to find the value of R2. In parallel connection, if two resistors are connected in parallel, we will be having 1 by Rp is equal to 1 by R1 plus 1 by R2, or 1 by Rp will be equal to R1, R2 is the LCM, denominator R1, R2, numerator R1 into R2, you will be getting R1, R2, R2 into 1 plus R1 into 1. Okay, then what is Rp? Rp is R1, R2 divided by R1 plus R2. R1, R2 divided by R1 plus R2. We know the value of Rp. Rp is 6. 6 is equal to R1 15, R2 divided by 15 plus R2. Taking this 15 plus R2 to the opposite side, 6 into 15 plus R2 is equal to 15 R2. 6 into 15, you will be getting 90 plus 6 R2 is equal to 15 R2. Okay. Taking the 6 R2 to the opposite side, 90 will be equal to 15 R2 minus 6 R2. You get 9 R2 is equal to 90. If 9 R2 is equal to 90, then R2 will be equal to 90 divided by 9, which is 10 ohm. Okay. So the required resistance R2 will be equal to 10 ohm. Okay. When 15 ohm and 10 ohm are connected in parallel, we get effective resistance 6 ohm. Okay. You can see that this 15 ohm and 10 ohm is greater than 6 ohm, which is the effective resistance. The combination is parallel combination. 5 resistors each of 3 ohm are connected as shown in figure. Calculate the resistance first between the points P and Q. Here we have 2 points P and Q given, and the second part between the points X and Y. Here we have X and this is Y. Okay. First let's consider this P and Q part. Here you can see that there is a continuous connection. This is the end of first resistor and the end of second resistor is starting from the end of first resistor, which means this combination, these two, 3 ohms, this and this are connected in series. So there you will be getting Rs is equal to 3 ohm plus 3 ohm, which is equal to 6 ohm. So between the points P and Q, you have another resistor of 3 ohm. Okay. Here we have another resistor of 3 ohm. This is point P and this is point Q. Now here, this effective resistance is connected in parallel. So when you draw an equivalent circuit, this is how it looks like. Okay. This is P and this is Q. Here you are getting 6 ohm. So across P and Q, now there is a parallel combination. We have to find 1 by Rp. 1 by Rp will be 1 by 6 plus 1 by 3. Which is equal to LCM 6. Here 1 plus 3 into 2 is 6. 2 into 1, 2. Okay. 1 by Rp. 1 plus 2 is 3 divided by 6. Okay. Therefore, Rp will be equal to 6 by 3, which is 2 ohms. Okay. So this part across P and Q, we are getting across P and Q, or between P and Q, we are getting the resistance value equal to 2 ohm. Okay. Now, the next part between the points X and Y. How to find between the points X and Y? This complete part is solved. Okay. We are getting 2 ohm. So, here this 2 ohm is connected to, the ends of 2 ohm is connected to first part to the resistor and the second part to this resistor, which means there is a series combination. This is how they are connected. There is a continuous connection, right? One end of the first resistor to the other end of the second resistor and the other end to the next resistor. So here we have 3 ohm and this part, this entire part is 2 ohm which we have determined, and this part is again 3 ohm. So how much do we get the RS value? 3 ohm plus 3 ohm, 6 ohm, 3 ohm plus 2 ohm plus 3 ohm, 3 plus 3, 6, 6 plus 2, 8. 8 ohms is the RS value. Okay. A particular resistance wire has a resistance of 3 ohm per meter. Find the total resistance of 3 lengths of this wire, each 1.5 meter long, joined in parallel. Second part, the potential difference of the battery which gives a current of 2 ampere in each of the 1.5 meter length when connected in parallel to the battery. Assume that the resistance of the battery is negligible. Internal resistance is negligible. Okay. Now the third part, the resistance of 5 meter length of wire of the same material but with twice the area of cross section. So these 3 parts we have to find. What is given? Given that for 1 meter of wire, the resistance is for 1 meter of wire is equal to 3 ohm. Okay. Now the first part, we have to find the total resistance of 3 lengths of this wire, each 1.5 meter long. Then what is the resistance of 1.5 meter of wire? If 1 meter of wire, it is 3 ohm. Then for 1.5 meter of the wire, it will be 1.5 into 3 ohm, which is 4.5 ohm. Okay. So 4.5 ohm resistance, 3 lengths are considered which are taken in parallel. Okay. They are joined in parallel. First, second, third. Okay. They are joined in parallel, each of 4.5 ohm. Okay. Now we can find the total resistance, the effective resistance. 1 by Rp is equal to 1 by R1 plus 1 by R2 plus 1 by R3. Here all the 3 resistors are of same resistance, which is 4.5. We have 3 resistors. Okay. We have studied a relation. Rp then will be equal to resistance divided by number of resistors. Okay. When all the resistors are having the same resistance, you can find Rp is equal to R divided by N. Here R is 4.5 divided by N is 3. Okay. 4.5 divided by 3, which is 1.5 ohm. Effective resistance in parallel is 1.5 ohm. Now the second part, B part, we have to find the potential difference of the battery which gives a current I of 2 ampere in each of 1.5 length when connected in parallel to the battery. Okay. So here each resistors are considered. The resistance of each resistor is 4.5 ohm. Then what is the potential difference V? We have Ohm's law. V is equal to IR. Okay. Here I is 2 and R is 4.5. 2 into 4.5 will be 9. Okay. 9 volt is the potential difference across each wires. Okay. Now the third part, C part, the resistance of 5 meter length of wire of the same material but with twice the area of cross section. Okay. We have resistance R is equal to rho L by A. When the length was 1 meter, we had the resistance 3 ohm. R is equal to rho L by A. So initially we had resistance of 3 ohm. R is 3 when the length was equal to 1 meter. Rho into 1 divided by A. Okay. 3 is equal to rho L by A. Rho into 1 divided by A. Now what happens? We have to find the new resistance when length becomes 5 meters. And area becomes twice, which means A dash, new area A dash will be 2 times A, new length L dash will be 5 meter. Okay. Therefore, the new resistance R dash will be equal to rho. For the same material, we will be having the same resistivity. Okay. Rho into 5 divided by 2A. Okay. This 5 and 2 can be taken out. Then we have rho into 1 divided by A. Rho into 1 by A is 3. Okay, therefore R dash will be equal to 5 divided by 2 into 3, which is 15 divided by 2, 7.5 ohms. Okay, 7.5 ohm is the new resistance. Understood? The diagram below in figure shows the arrangement of 5 resistances connected to a battery of EMF 1.8 volt. That is the voltage of the battery. Calculate the total resistance of the circuit, and the second part, the reading of ammeter. Reading of ammeter gives a current through it. Now first we will have to find the total resistance. So here we have two parallel combination. This is the first one and this is the second one. Okay, first we will be solving across XY. Between XY, what is the effective resistance? So here we have R1 and R2 connected in parallel. Therefore 1 by Rp equal to 1 by R1 plus 1 by R2. 1 by Rp is equal to, put the values, R1 is 10 and R2 is 40. Okay, 1 by Rp is equal to, here when you take the LCM you will be getting 40. Okay, 10 into 4, 40, 4 into 1 plus 40 into 1 is 40, 1 into 1, 1. Okay, which is 5 by 40, or Rp is equal to 40 divided by 5, which is 8 ohms. 8 ohms. So this part when solved you will be getting 8 ohms. Now the next part, here we have R3, R4 and R5 connected in parallel. Therefore, we will be having 1 by Rp equal to 1 by R3 plus 1 by R4 plus 1 by R5. 1 by Rp is equal to 1 by 30 plus 1 by 20 plus 1 by 60. What is LCM? When you take the LCM, you will be getting 60 in the denominator. Okay, 30 into 2 is 60, 2 into 1 plus 20 into 3 is 60, 3 into 1, 3 plus 60 into 1 is 60. Therefore, you will be getting 1. That is 1 by Rp. 1 by Rp is equal to 2 plus 3, 5 plus 1, 6. 6 by 60, which implies Rp is equal to 60 by 6, and that is 10 ohms. So, when you solve this part across AB, you are getting 10 ohms. Now, how are these two connected? When you draw an equivalent circuit, you will be having, this is the first part, then you have a battery, then you have the second part. Here we have the ammeter. So here you can see this is a series combination. Ammeter comes in between, but there is a continuous flow of current. Current flows continuously through this. Okay, this is a series combination. Here you have 8 ohm and this is 10 ohm. Therefore, total RS, effective resistance RS will be equal to 8 ohm plus 10 ohm, which is 18 ohms. So, 18 ohms is the effective resistance. Simplified circuit, here you have 18 ohm resistor, 1.8 volt battery, an ammeter. Okay, we have to calculate the ammeter reading, which means we have to calculate the current value. So, B part, according to Ohm's law, we have V is equal to IR, which implies I is equal to V divided by R. Just put the values. What is V? V is given EMF of the battery, which is 1.8 volt divided by effective resistance in series, that is 18, which is equal to 0.1 ampere. Okay, 0.1 ampere is your current or the reading that is shown in the ammeter. Okay, or you can write this as 100 milliampere. That's all for today. In today's class, we have discussed what electromotive force is. We have discussed about terminal voltage, internal resistance, and the combination of resistors. We have also solved problems related to it. Hope you all enjoyed the session. I'll be asking you to solve many problems which are similar to this. I'll be back in the next session. Until then, stay tuned to Learn Hub. Learn Hub free hai, par best hai. Thank you.